translation of
Okay.
Daniel. No, Amber Alert goes over vibrations.
Okay, let's jump into it. Let's finish off the application section, which I want to talk about one more idea, which we have mentioned before, but I just want to go over it because there still seems to be some questions and misunderstandings. How about growth? There are two important kinds. I mean, there are many kinds of growth, but there are two ones that are particularly important and widely applicable. We call it linear growth. That's when something increases or decreases by a fixed amount per unit time. Like if you're adding up how much money you're paying on your Netflix account, that's the linear growth, right? They charge you the same amount of money every single month. And there's exponential growth, right? So essentially linear growth means it grows like a straight line. In other words, it always has a constant slope. So the differential equation that describes that would be something like P equals a constant, which is not even interesting enough to be mentioned in this class, but it's a thing that you would study in like algebra class or something. Exponential growth, though, this means you increase by a fixed percentage per unit time. So you're not necessarily increasing by, say, 10, but rather you're increasing by 10%. And that is different. So if you started out with $100, after 1 year, growing by 10%, you'll have 110. The following year, you're actually going to grow by more than $10, because now you take 10% of 110. And so you add a little bit more every year, and so it keeps getting bigger. It grows a lot faster. So that one grows like with an increasing slope. It increased by that amount 1 year, then it keeps increasing by more and more over time. And the way that we model exponential growth is P equals RP, and where R is the percentage growth. So you want to find out how fast the thing is growing, tell me what it currently is. I'm going to find a percentage of that, and that's going to give me the growth, the rate of growth of an exponential growth function. So that we pretty much took as a definition. So we pretty much define, we say P T grows. The reverse of that, we call it decay. Decays exponentially. If P prime equals RP, where R equals some fixed percentage. Written in its decimal form. Now, one other way you can modify this is that if we assume some change in P modeled by a constant fixed amount, H, we can obtain, well, P prime equals RP plus H, right? So here you have something that's on its own is growing exponentially, but something is changing it at regular time intervals by the same amount H. And so we can obtain a differential equation like that that describes the rate of change of P, how is it growing. Now, in population circles, these two models have names. This one is called the Malthus model and the Harbison model, but they are more general concepts and they do apply to things other than populations. Because not just populations grow exponentially, a lot of things grow exponentially. And so, and you can even think of this one as a special case of that one. It's just that h equals 0 here. And many things exhibit this kind of growth. Including, but not limited to, not an exhaustive list, populations. And anything, usually in our context, money, that is compounded continuously. So that's where that kind of comes from. How did we see this? Well, if you look at the compound interest formula, well, that looks something like A equals P 1 plus R over N to the NT. Right?
It's a general solution to the other one, right?
It's a general solution to, it's something slightly different from that, but pretty similar. But this is like compound interest, where you're measuring the interest gain by something, where interest is being gained on top of interest. This is an N here. So P is your initial investment or principal. R is the interest rate that it's growing at. N is the number of times it's being compounded per year. T is the time in years. R being your annual interest rate. You can actually measure the balance in the account by this equation. It's called the compound interest formula. Now, compounded continuously means we let n approach infinity. Okay, so the amount of times they're being hit with interest on this account, if we let n approach infinity, you will notice the following happening. And set set x equals set x equals n over r. N over r. Yeah, that's fine. I'm going to set n equals n over r. And notice r is a constant. Now, as n approaches infinity, you'll notice that x is approaching infinity. And so, to compute which is pretty much a thought experiment, what would actually happen if we actually let n approach infinity of this thing here? Pretty much, almost. What we have is, you can see it almost clearly. I made the substitution to see it even clearer. What you'll notice here is that, well, if I change the variable to x's, limit as x approaches infinity of p times 1 plus, well, this would be 1 over x. And since my x is n over r, my n is r times x. So I can change this to r times x times t. And what we can do is, this is the limit as x approaches infinity of 1 plus 1 over x to the x to the rt. And that's the limit definition of E. And in fact, this is kind of where E came from. This was the question that Euler was considering, right? So Euler considered the question, if we deposit $1 into account and hit it with 100% interest rate, compounded an infinite number of times per year, how much money would the account have after a year? And because people know how exponential functions are, they grow rapidly fast. They think, what? You'd have an infinite amount of dollars. It turns out, no, you have considerably less than that. You'd have $2.72 at the end of the year under those conditions, which is an approximation for E, and you worked it out to multiple variables. At the end of the day, this became PE to the RT, right? So that's because this became E here. And limits passed through continuous functions, all the calculus stuff is accounted for here. So now, if you consider P prime equals RP thing and realize that, hey, that is a separable differential equation. Integrate both sides, where ln of P equals RT plus C, and so raise those to E. You get P is equal to C e to the RT, and you'll realize that this C here is going to be your P naught, which is the P over here. You're going to recognize that, hey, that thing is actually the solution to this differential equation. So now we know it all ties together. Whenever someone talks about something being compounded continuously, because just working backwards from Euler's formula, we realize that it also solves this differential equation for something growing exponentially. It will fulfill the same exact differential equation. So in your homework or wherever you see something compounded continuously, it turns out it is governed by this differential equation, and the solution will look like this, where that is the initial value at time equals 0. Now, of course, as I said, you could be changing this by some constant value, and you put that as plus h, right? So if you have an account growing compounded continuously, and you're depositing $100 every month, you just put plus 100. If you're withdrawing $500 every month, put minus 500, etc. Right? And you can solve a new differential equation. It's going to have an extra term over here, and you just run with it, right? But this is going to be the basis, the RP plus H. Someone was doing exactly. We're going to talk about that tonight. I just want to rush through this. So at the end of the day, that's what I want you to know. The takeaway for this for populations. And compounded continuously accounts use P prime equals RP plus H. Unless indicated otherwise. There are other models for measuring stuff like populations, and your homework does have some of them, but in those other situations, the homework problem actually tells you what differential equation to use. So you have the logistic model, you have all that other stuff, but otherwise, if you see a word problem, it doesn't actually tell you about a differential equation, but it mentions like a population is growing at 3% per year or whatever. You're starting here. So just want to make sure that at least is clear. Just to bring it down to 391 level, that's how you want to know how this thing applies. Secondly, what else did I want to mention? Okay, so here P equals quantity that grows exponentially. R is the percentage growth rate. So that would be the interest rate on the account, or what percentage of population is growing by per year, or per whatever unit time. T is time. It's usually in years, but time time units must match for your interest rate and your whatever units. Right? So if they tell you interest is being charged every month, measure time in months. If interest is being charged every year, measure time in year. Make sure these units are always the same. And H is a fixed, constant amount. P also changes by per unit time. Same units, match up all the time units.
Do we have to use the decimal form?
Yes.
Because I noticed in the homework that some of the questions wanted integers as answers.
Take it around,
Yeah.
Well, you would use the decimal form of the original equation, but your answer is just round to integers.
Wait, I don't get why.
Because how would I get an integer if I'm just using the ratio of something?
I don't know what you mean.
So like you would ask me to put the answer, and if I put the ratio of like 2 11s, like ln of 300 over 5, for instance.
Okay?
And that came out to be like a decimal thing. It wouldn't accept the answer. It made me go back and change it to the nearest integer value. But I would only be able to do that with like a calculator or something. So.
Okay. I don't know if it asks for something, but in general, you can use calculators on homework.
Okay, just making
Not-
sure.
that's not objective. Right, so if you're doing it on a test, then I would accept your answer with LNs in it.
Okay.
I don't understand why there has to be decimals. Like, why can't you just leave something as 2 over 100 as opposed
Yeah,
to
there was so much.
Zero point
So
zero
upset
two.
at that.
Oh, you mean you would have to leave it as 2 over 100 as opposed to 0.02?
Yeah, like,
No, it would, like if you try to.
Except the calculator.
okay, so like, no, I'm saying like you just said that it has to be decimal, right? But I don't understand why you can't just leave it as 2 over 100 as opposed to 0.02.
You could.
I think you can't use it as a percent.
What I don't want you to do is if something says 5%, don't put the number 5.
Oh.
That's what I read.
Okay, alright.
Right? Put 0.05 or put 5 over 100.
Alright.
They're both the same thing. So I usually just say the decimal version because it tells people that they don't ignore the percentage sign and factor the percentage sign. Okay. So this leads us to example 1 from the handout. So let's just finish this once and for all, finally. We did everything else. Huh? No, we finished everything else. We did all the time problems, and then we did the new ones. The same old. Okay, suppose that a sum S0 is invested at an annual rate of return R, compounded continuously. Once they mention compounded continuously, that's the thing you imagine in your head. It means that differential equation applies. Find the time t required for the original sum to double in value as a function of R. So, that's 8. Want time to double. Well, if we're starting out with P prime equals RP, okay, so this doesn't say that something was being added extra, right?
So no H.
So there's no H here, right? So it just says something is invested and it is has a return rate of R compounded continuously. So you're going to have this. Now, ultimately, you're going to solve this differential equation as separable. Let's skip all the steps and get P equals P naught e to the RT. Or for them, they said S naught, whatever. So now what you're going to do is you're going to want to find to double. That means what should this over here be?
2S0?
Well, 2S naught. Divide both sides by S naught. You take ln of 2. That's equal to RT. So your T equals ln 2 over R, or what they call big T in this question. That's it. By the way, there's nothing special to double here. Anything that grows exponentially, the time to double will be ln 2 over R. The time to triple, ln 3 over R. The time to quadruple, ln 4 over R. This actually will follow.
Can you explain that again? Just a little bit.
Come again?
Can
What do you see how I got this?
You said the double, yeah, you said like when double.
Yeah, so double is why we have the 2 here.
Yeah.
If someone said triple, how long is it going to take to triple? It's going to be ln 3 over r. Quadruple, ln 4 over r.
Like whatever that function has to be, so like ln the doubles ln 2.
Yeah, and that form will work. So normally when I'm teaching Calc 1 where they do this, I just tell my students, just memorize that. ln 2 over r is the time to double.
That's a consequence of the E that's secretly in there, right?
Yeah, but I don't tell the calculus. Like this is the form for the time to double. Right? So that's it. That's part A. B, determine T if R is 7%. You're just gonna plug it in. B. T would be ln 2 over 0.07. Good enough for me. Find the return rate that must be achieved if the initial investment is to double in 8 years. Well, again, I'm going to use T equals ln 2 over r, and I want 8 equals ln 2 over r. This means the investment rate should be ln 2 over 8, whatever that is. D. Okay. If $1,000 is initially invested with another $500 invested every year, how long before the balance reaches $55,000? So,
It's kind of like a different question equal to,
We have to take into account the H.
yeah, but we have to take into account the H now, because here you're investing another fixed amount per year. So that's not based on some percentage, that's a fixed amount, that's an H. So for D, you kind of have to start over. You're going to start over with P prime equals RP plus H. And in this case, this means that your P prime equals, did they tell you the,
It's the same rate.
Should we assume 7%?
I think we'll assume 7%. So that would be the equation that you start with.
yeah, and the 500 just gets a T attached to it.
Yeah, it's just, well, would it?
It's just automatic per unit time. It's like embedded in 500.
Not really. We derived the general formula to this, and it was multiplied by a constant, but it was like the H over R or something. I forget. Anyway, so the trick is this would be separable. Normally I tell my calc students factor out the 0.7 first before you move over here because I expect them to forget that they have to use the chain rule here. No, you guys aren't going to forget. So this is 1 over 0.07 ln 0.07 p plus 500
Okay, yeah, the 500
equals t plus c. And so what you end up with here is 0.07 p plus 500 is going to be c e to the 0.07 t. And so ultimately your p is going to be equal to ce to the 0.07 t.
How'd you get the rate on top of the E again? Or is that just from?
We assume it was 7.
You,
Oh, okay.
you
Yeah.
multiply with
I multiply by 0.07
Oh, okay, I see it now, I see it.
and
Sorry.
then
And then
I
you eat it, and then it goes on top
eat
of
both
the thing.
sides, it went into the power, the plus
Yeah.
c here comes down as the constant, then I have this, now I just subtract the 500, and then divide both sides by 0.07, I still keep the same c, even though technically, these are all different c's here, but we're going to solve for it at the end of the day.
Is there any time that having C's be labeled and distinct ever matters? Like in any
For us,
case?
no.
Oh.
What does matters is there are times when there will be several constants, and you have to distinguish between those in a single problem. But if it just has one arbitrary constant, just keep writing as the
Like
same
in
guy.
all of mathematics, it never matters, or?
I would say any situation where at the end of the day you're going to plug in a number that makes that thing work out, it's not going to matter. So now,
Shouldn't you be dividing everything by 0.07?
yes. So I divided C by 0.07, but I just call it another C.
Ah.
That's what I'm saying. So I'm just keep calling it C to save me writing down a bunch of things happening to this C.
That's so interesting.
Right? I don't want to have to write like e to the c divided by 0.7. It's just a constant, right, which we're going to solve for eventually. In fact, we can solve for it right now. We know that the initial amount is 1,000.
So 1,000.
So this means 1,000 is going to be equal to c
minus 500.
e to the to the 0. It's going to be minus 500 over 0.07. Now you're going to solve for the number that makes that happen. So this is going to be 1,000 plus 500 over 0.07. That's equal to C.
If you got a 0.
For the 1,000.
Where?
1,000.
He's trying to rob me. It's not enough zeros.
You got what works. I sat there
Then
on
we're going to
the
find him in his room, dead, trying to use Newton's equation to figure out when he was killed.
You
Yeah.
can also use the other method to solve the differential equation, right? Where you
Which
bring
method?
the dp over dt, you bring the negative 0.07p plus 500. I think it was like the first order differential equation where you get the mean.
Oh, yeah.
Oh, yeah, it's also linear, yeah.
Okay,
But I'd probably try separable first.
alright. But like it will still give you the same.
You would get to the same answer. I think it'll be a little bit longer though, but in theory there's nothing wrong with that. I think after I show you, after we go through exact, what I'm going to do is I'm going to like give you guys a strategy or a hierarchy.
Oh, okay.
So it's like, okay, if you have a random first order differential equation, what do you try first and second? And separable is higher in that list than linear. So you try separable before you think linear in general.
Because when you try to do it on the homework, it gets stupid long. That's why.
Yeah,
The
so.
integrating factor.
Yeah, the integrated factor.
Well, integrated factor goes with the linear.
Wait, what's the current, like, the hierarchy? Like, do this for now.
Well, I'm going to tell you.
Sit tight.
So, so that's your C. So really, the balance in your account looks like whatever that number is, 1,000 plus 500 over 0.07 e to the 0.072 minus 500 over 0.07. And so how long before the balance reaches 55,000? So,
55,000. All that.
right, we want 55,000 to be equal to 500.07 e to the 0.07 t minus 500 over 0.07. So this is going to mean your t is going to be equal to, can we do this one shot?
55,000 minus
55,000
plus
500 over 0.07.
divided by 1,000 plus 500 plus 0.07, and that's the log that,
And then I'm going to take the log of this
and divide it by 0.07.
and then divide by 0.07.
And then you're going to cancel the 500.
And then we're just going to wait.
Like in a test, you leave it like that. I'm not going to encourage it.
I'm about to commit a
But if
blast.
anyone that has a calculator, just for fun.
Yeah, 500 over 0.07.
Yeah, why don't you just cancel it?
Tell me the whole thing, like the whole, like what does this all this? Just for fun.
Yeah. Get lost in the parentheses.
It's pi.
Yeah, Webwork would ask for this. I'm dead serious.
We got 29.02.
29.02.
Incorrect number.
Probably asked for like 6 decimal points.
I sat there for like 20 minutes getting submitted.
And yeah, that's pretty good. Starting out with $1,000 and only putting $500 a year for 20 years and you end up with 55,000. That's a pretty nice growth rate.
There's also inflation.
I mean, we do better in the market.
You can probably do better in the market, at least before taxes. Yeah.
I have a question, top word, where you wrote 0.07p plus 500 equals CE, right there? Second, yeah, right here, where you drew the arrow now, right?
Yes.
You subtracted 500 and divided by 0.07.
Yeah, so I moved this over here to get minus 500,
Are you supposed to?
and then I divided by this 0.07. Yeah.
You didn't write 0.07 over the whole thing. Isn't this-
Oh, well, I just split it up. I divided the 0.07 into the C and the 0.07 into the 500 separately.
Oh, okay.
Okay, that's done. Let's talk about this. This is going to be pretty cool. And it might help you out with your other class if you are in 392. A little bit. Computation. I think this is 2.6. We're looking at something called exact equations.
I thought these were exact.
Yeah, fucking exact.
It's a different kind of exact. And they're integrating factors. So, of course, we all remember our Calc 3 very well. And there, at some point in Calc 3, we'll learn about the multivariable chain rule. It tells us how to find the derivative with respect to x of a level curve. Like, so let's say we have a function here. We have a surface described as a level curve, like some function of x, y equals c. Now, suppose you want to go through and you want to find dy dx. Right? So you want to find the derivative of y with respect to x. Okay? So the chain rule basically tells you what that's going to look like. So this is by the chain rule. This is going to be the partial of f with respect to x times dx over dx plus the partial of f with respect to y times dy over dx equals 0. Differentiate both sides. And you kind of cycle through all the variables. Now, technically, because of how useful the Leibniz notation works, is that guy would cancel. But what you can do is here,
How come we're doing PDEs until the end?
huh?
Now we have partials in there?
Yeah, that's a partial, these are partial derivatives here, which can be written as well, you can write this in a couple ways. Well, you can write the partial of f with respect to x plus fy times y prime equals 0. Or you can write it as the partial with respect to x times dx plus the partial with respect to y times dy equals 0 by just multiplying through by dy. Now, what you should notice here is that if I look at this,
Oh,
Or the linear?
Not really. Well, it depends on what the functions are. We don't know if it's linear because we don't know how these functions look. Right? If they're functions of y's with like powers in it, then it's probably not linear. But it does have a derivative in it. Your partial with respect to x is just another function, right? So is your partial with respect to y. And then there's a y prime attached to it. So this thing, which I can call, let's say, 1, but 1 is a differential equation. Actually, we call that 2, because otherwise it's going to seem very silly. And what we've discovered accidentally is that 1 is its solution. What is 1? This guy over here. Remember what the point of solving a differential equation was. We had an equation that had derivatives in it. We wanted to get to a situation where that equation is true based on some function that has no derivatives in it. This doesn't have any derivatives in it. And it makes that function true. So, looking backwards, that was the solution to this differential equation. So, what does that mean for us? This means if we have an ODE that has the form then its solution is, well, the F. Here's an example. Consider. That's the most scary word in mathematics. Consider this. It's usually when someone's gonna like pull something out of their, rabbit out of a hat. Like, where did that come from? Why would I be considering this? What? Okay.
It's like they're assuming you don't know.
It's like they're assuming, like, of course, just consider this. You clearly see where this is coming from. Okay. So consider this equation. And by the way, I think either this or something very similar to this showed up on a quiz or two. So let's say I gave you that differential equation. Now, of course, you could divide by dx. So there's a differential equation. Now, here's what I also want you to notice. And consider the function so I'm going to write down the function here. X squared 2 plus x squared 2 plus x. Equals c, some implicitly defined function. I were to take the partial with respect to x of this function, what would I get?
X plus.
2yx, no, y squared, 2
Y squared
x,
or
y
y
squared, plus x,
Oh, yeah. xy squared,
Plus
right? Because it was
X.
partial means you think of the y as a constant, differentiate the x's. So the 2 comes down, ignore these constants, they'll cancel, you get xy squared.
plus x,
This
plus x,
plus x
plus 1,
plus 1.
plus 0.
And look at the partial with respect to y. What would I get?
X
X squared y,
X squared y.
that's it, is equal
That's
to.
it. But notice that this guy is that. And this guy is that.
Snap.
So that solves the differential. All right, good night. That's it.
That's all.
You guys know everything about it. Yeah, that's the solution. Because I noticed that this function has the properties that if I take the partial with respect to x, I get the thing that's attached to dx, and if I get the partial with respect to y, I get the thing that's attached to the dy.
Why did that happen?
Accident?
Accident? I just came up with this. No, let's actually, that's the question, isn't it? How did you come up with that function? Why were you considering this in the first place? I considered it. Okay.
Yeah, we have to consider a lot of things.
Are you gonna give us the questions and the answers tomorrow?
No.
Are we gonna have to make up?
So here's what we're going to do. It turns out that this is a special kind of differential equation called an exact differential equation. And there's a way to actually get to this function. So what happened?
Oh, we have to integrate in terms of each letter, right?
So xy squared plus x plus 1 dx.
Oh, it's like finding the scalar potential.
Okay,
right?
so these have a special form. It means you can write them the standard notation is to call the guy in front of dx some function n, say m of xy times dx plus n of xy times dy equals 0, where m is equal to the partial with respect to x of some guy, and n is equal to the partial with respect to y of some other guy, of the same guy, right? And the solution is given by fx, y equals c all the time, okay? Now, a couple important questions. How do you know that you're actually looking at something that looks like this? And 2, how do you go about finding the solution without considering? Like, what is that?
I think you have to, it has to be a function of 2 variables for both.
Well, that's by assumption, yeah. We're thinking of them as 2 variable functions, whether or not they're here.
And then to figure out the solution, you have to integrate the dx portion of it in terms of x, and then the dy portion in terms of y on the other side. And that should leave us with the function.
And then you sum up all the.
And what do you do about the constant of integration?
Oh, you
I have
sum.
no idea.
Okay. So let's actually do this. Now, we assume that m and n are continuously differentiable. If they're not, you have to be a lot more careful, and it's outside the scope of this class. So don't worry about that. This means that you can differentiate them and you get continuous functions in whatever region you're considering. And this means something else that we all remember from Calc 3, except we never remember how to spell his name. I want to say Clarister. You remember that one, right? That says if f is continuously differentiable, then the order of partials don't matter. Right?
Yeah.
There's a theorem that told us that from Calc 3. So, if your n is the partial with respect to x of something, and your n is the partial with respect to y of something, then what you can do is you can find the partial of this with respect to y. That'll give you x of xy. And then the partial of this with respect to x will give you fyx. But it turns out that that should be equal to fxy. So we can determine.
I just want to make sure my notation is correct. That's the derivative of y in terms of x is equal to the derivative of x in terms of y, right?
No. This means you took the partial with respect to x, and of the result, you take the partial with respect to y.
Okay.
So it's a second derivative.
Okay, I got it.
So you differentiate first with respect to x, then you get an answer, differentiate that with respect to y.
So
And this one is you differentiate with respect to y, then differentiate with respect to x. And if your function is continuous, you'll always get the same thing no matter what order you do it.
Okay.
Right? You can always switch the orders.
I got it. Thank you.
Now, what that means is then, if I take the first part differentiating with respect to y, and the second part differentiating with respect to x, they should both equal the same thing. That's going to tell me that this guy, the original m, is the partial with respect to x of somebody, and this guy is with partial with respect to y of the same guy. Right? So, it turns out that's the check. We can determine an equation is exact with this check. Let's actually look at the example before. Now let's look at this again. Yes.
Are discriminants going to, are they going to be part of any of this lesson?
Come again?
Discriminants.
No. Okay, so now look again at this differential equation. Now if you start going through and labeling the pieces, this guy here is going to be your m. This guy here is going to be your n. How do I know that something like this even existed? There's this function that has the properties that I wanted. Well, take the partials. Note, if I take the partial of m with respect to y, what would I get here?
2xy.
That's it, right? And then if I take the partial with respect to x, what would I get?
2x.
2x.
Oh, I thought you meant that.
So this means my equals next. And that means exact. That means there is an f. So that f equals c solves the ODE.
Yeah, it's like potentials.
Yeah, Scalar
It reminds me of
Potentials.
potentials.
It's exactly like that.
Oh, is it that?
It's exactly. My computation is exactly the same thing.
Okay.
So it's like a conservative vector field. This is how you can find the scalar potentials. So if you pretended this was a vector, where this is the x component, that's a y component, but you're thinking of it as a vector field, and you want to see, is it conservative? You'll do what? You'll differentiate the first component with respect to y, second component with respect to x. If they're the same, it has a scalar potential. And then you go through and find it. That's what you do in 392. Now, I'm going to summarize this pretty soon. For now, we're just on this journey, kind of figuring out how this thing is going to work out. So, you can be faced with something. Now, in general, if you look at something first, you're going to think of a bunch of things first. Is it separable? Is it linear? Is it homogeneous? This one, none of the above, right? It's not separable. It's not linear because there's a y squared. It's not homogeneous because of the x and the plus 1. So because I'd be able to factor out a k cubed here, but only a k from there and nothing from there. So that's not going to work. It doesn't actually obey any of the rules that we had before. However, if I take the partials in this way, it checks out. So this is just another method that we can use in another situation. So now, how do we find this f? There are a couple ways. Your textbook goes through one of them, which I probably ignore. I might tell you if I'm bored, but I don't want to show you. So a better way to do it is to kind of do what Chris suggested earlier. Actually take the integrals. If your n is actually the partial with respect to x of some function, then that means we can think of your f as the integral of n with respect to x. And if your n is the partial with respect to y of some function, that means that function will be the integral of n with respect to y. Right?
Is there another way to do this other than these two specific ways?
Well, I'm showing you one specific way at the moment. So this is one way to find the f. Now, let's deal with the constants of integration. If your constant of integration is actually a legitimate constant and it doesn't depend on either one of the variables, then he's going to be absorbed into the c. So what you probably want to worry about is, what if there was a function of y over here that when I differentiate it with respect to x, he gets wiped out and I don't even get to integrate it, right? And what if there was a function of x over here that when I differentiate with respect to y, he got eliminated so I don't even get to integrate it, I don't know he existed. It turns out that all those guys would get caught in the other guy. So if there was a function of y over here that got eliminated when I differentiated with respect to x, he'd show up down here, right? Vice versa, anyone missing from here is going to show up there. So it means that I can do these two integrals and not worry about what the arbitrary constant of integration actually looks like, because anything that's missing from one, I'll pick up in the other. And anything that's purely a constant, I'm going to move it to one side and put it inside that c anyway.
What about if it's in R3?
Then you have three integrals and the same thing will work.
It works for any number of
any number of variables, yeah. So if you had a dz, you'd worry, what if there were functions of x and y? Well, the other two is going to pick them up. And if you're at the dx, what about the functions of y and z? Well, the other two would pick them up, right? Anything missing from one is going to be caught in the other. So you don't have to actually worry about it. The method in your textbook goes through the whole process of worrying about what the constant looks like. What if it's a function of y? Then we have to try this and blah, blah, blah. But you don't have to actually care. That's just something extra. So here's how we'd actually go through and find it then. So again, we're looking at the same guy. So, given that xy squared plus x plus 1 dx plus yx squared dy equals 0, and partial with respect to y equals a partial of n with respect to x, where this is your m and n respectively. In 392, it's exactly the same discussion, except they call these P and Q.
Yeah, or we're gonna do like
Right, so from Green's theorem, where it's like the dp dy minus the q dx, it's the same thing. Okay.
Okay.
So, once you notice this, what you can do is you can immediately say the solution is f of xy equals c, where f is going to be equal to the integral of this with respect to x, because I differentiated with respect to x to get this part. So I'm going to integrate it with respect to x. And at the same time, f is the integral of this with respect to y, because I differentiated with respect to y to get that.
With respect to it with respect to partial y and partial x, or dx?
Yeah, but it's gonna be the same thing. Yeah, so this means your function must look like what? Well, if I integrate that with respect to x, what am I going to get? X squared over 2 times y squared plus x squared over 2 plus x plus some constant. Now, again, this might be a function of y. We don't know, but we don't actually care. Because if there was a function of y, when we differentiated him, he's going to show up down here. So I'm going to get to integrate him with respect to y and find him back. And your f is equal to integral y x squared dx dy. So you get x squared y squared over 2 plus some other constant, which is potentially a function of x. But again, you don't actually care. So what you're going to do now is you're going to pick out all the unique functions. These are the same functions, so you don't want to copy anything twice. So part of the function is x squared y squared over 2. So we're going to write that down. I'm going to ignore that if it repeats. Another part of the function is x squared over 2. And another part of the function is x. So I write down all the unique functions that show up one time. And that's all the functions that show up one time. And set that equal to c. That's your answer.
Oh, wow. So it's kind of like when you're doing the potential, only you don't care about whether the constants are a function of a particular variable.
Yeah, so it's like if you have this is p and q. You know it's conservative. You know it's conservative if partial p with respect to y equals partial p with respect to x. And you can find the potential function by integrating the p with respect to x and integrating the q with respect to y. And then f equals c is going to be your potential function. Same.
Okay, but easier.
Yeah, you integrate.
Just 1 second, could you explain again why you cancel the x squared, y squared, and y, and you just kept the y?
Well, it's the same function.
Yeah.
So if I write this down twice, I'm actually doubling a part of the function.
Okay.
Right? So any overlaps, you ignore the overlap, you just write this down one time.
Okay.
Right? Because I'm not finding 2 f's, I'm finding 1 f.
And then pretty much the d just gets...
Yeah, I ignore them.
The c, right?
So basically, what you would realize is that the d here actually includes the x squared over 2 and the x. But when I differentiate with respect to y, it got lost. But they actually show up here. Similarly, if there was any x's down here that got lost, they would have showed up there. Yeah.
If there's actually constants in f, like that. Oh,
I moved them all over here anyway. Yeah, so that's kind of it. Let's summarize, and then we'll do a bunch more examples. I don't think we'll get to the integrating factor part, but yeah, we went on a kind of journey here, so let's just tighten it up, make sure you know exactly what should I remember from the last 30 minutes of Jhevon talking. Right? What should you actually get through your head? Okay, so there is something called an exact differential equation. Now remember, at any given time, you want to know 2 things. What form is it, and what's the algorithm to solve it? So here is the form. Right? What does an exact differential equation look like? Well, it's going to be some function times dx plus some other function times dy equals 0. If you can rearrange your differential equation to have that form, where the partial of n with respect to y is equal to the partial of n with respect to x. So that's the form. Right? That's how you're going to know when you're looking at something that this strategy is going to work. I can spread it out like this, something times dx plus something times dy, where the thing in front of the dx, if I take the partial respect to y, is equal to the thing in front of the dy when I take the partial respect to x. That will work by Clairaut's theorem. And now,
But that's an interesting algebraic too, right? Like, it's a pretty unique form.
yeah, it gives rise to a differential form called an exact differential form, which is why we call it an exact differential equation. You know, you can't get too creative with naming stuff around here. But yeah, it's right up there with like the Laplacian and all these things you always hear about. There's another nice differential form called the exact differential form, and it looks like that. Exactly like that.
Yeah,
Damn, I can't believe I missed that fun. That was a good one. Next time I'll do it.
it wasn't my
It looks exactly like that. Exactly. Okay. Now, what is the strategy when you realize that this happens? Right? So you need to know the form, and you need to know how to actually solve it. And the strategy is pretty simple. Find f where f equals the integral of m with respect to x, and f equals the integral of n with respect to y. Ignore arbitrary constants. And sum all functions that show up once. And the solution is given by f of x, y equals c. Where, yeah, that is going to be the sum of functions that appear in the last step without repeats. So if something shows up multiple times, you write it down one time. And that's going to be the answer. That's the solution to the differential equation. So, exact differential equations, they look like that. You know you're looking at one because it behaves like that. Once you find that is the case, this is your strategy. You're going to integrate the dx part with respect to x, integrate the dy part with respect to y, collect all of the unique functions that show up, add them together, equals c, that's your answer. And that follows automatically from the multivariable chain rule. A lot of things follow from the chain rule.
Why don't we do that example on this page?
I'm going to give you several examples. So for this section, we have tons of examples.
Is there gonna be homework about
1, 2, 3, 4, 5, like 7 examples for this section. Yeah.
Could you have done it the other way around? When you essentially get the same thing?
The other way around, what do you mean?
As like starting with,
The names don't actually matter. It's actually very important that whoever is attached to the dx, whatever that is, that you have to differentiate with that.
what I'm saying is, you could have done it the other way around.
What do you mean?
In the last step without repeats, in the green.
Starting out first with differentiating with respect to y, that the function there.
No, if you differentiate this with respect to y, no, that's. You have to differentiate with respect to the variable. To check.
The difference between a transcriber and a translator is that a
The integral
transcriber
of
doesn't
that
have
side
skill.
with respect to y.
No runs
If you're starting out with that.
Yeah, if you did that second one first, you'd still get the same thing.
Yeah, we can
Actually,
You mean like doing this integral before that one?
Yeah, we have to do both.
Yeah, it doesn't matter. It doesn't matter the order. You have to do all of them. And you just write down what shows up once. examples. So that's the first one. I have two more examples, but that's for the integrating factors section of this chapter. So let's run through one quickly from start to end without any lengthy explanation, so you can actually see how it actually looks to actually get through one of these.
Let's see.
And again, something shows up on a paper, you're going to think all sorts of things first. So you probably think, oh, is it separable? It's not.
Homogeneous because of the y over x, that's what I think. But then,
yeah, but you don't have it here or here. Right? Homogeneous means it can be purely a function of y over x, which means you have to be able to see a y over x in every single component, which you don't. We're in section 2.6, so it's probably exact. So what you'll do is you'll call this your m, you'll call this your n, and what you're going to do is you're going to do a check. Now, I'm like I said, I'm going to do a blurb where I talk about all the methods that we've covered so far, when to choose which, that kind of thing, how you would look for them. So I would check. If I take the partial of this with respect to y, I would get
6.
That's zero.
plus nothing, that's 0. And if I take the partial with respect to x,
1 over x.
Well, I think we use plus 6.
Wait, is the
I'm taking the partial with respect to y, so that's a constant, so it goes to 0. Now what you notice is that that's equal. That means exact.
Is the minus 2 included in the other x?
Yeah, no.
Oh, it's like separate, okay. Alright.
Like it was included, I put parentheses. So this is exact. So what I'm going to do is I'm immediately going to say something like, just integrate this with respect to x, which is going to be what?
ln ln of x times.
Y times ln of x plus 3x squared.
plus some constant. And here, you notice that we can ignore this. Can ignore since our x is greater than 0. Then I'm going to look at the integral of the second component with respect to y. Integrate this with respect to y, well I get y ln x
Minus 2y.
minus 2y plus some other constant. Now, all I do now is I'm going to pick each function that shows up once.
Y ln of x plus 3x squared.
Y ln x
Minus 2
plus 3x squared minus 2y. We'll see. That is the implicit solution for our differential equation.
Is there gonna be cases where they ask us to solve for y?
This could be a case where we can solve for y.
Yeah, that's not too bad.
That's not too bad.
From both sides and then pull out
Yeah.
y.
So y would be here like minus 3x squared over ln x minus 2.
Wait, no.
C.
No?
Yeah.
But normally it probably wouldn't worry about it.
Oh, yeah.
Oh no, the
But
y
that's
prime.
basically it.
We gotta move the y dx to the side, y to the right, and then multiply, right, to get the dx attached to it.
Well, that's for you to figure out. We're out of time.
Oh man.
So, try the rest. Yeah, so there was one homework due tonight that I pushed to tomorrow, and the homework for 2.9, I believe I pushed to Friday.
There's no homework for day 6.
No, you see it pretty
Just
good.
do the best
It was like midnight last night.
Wait,
I wanted
that's
to
not
take
how,
it.
Well, there was some work right
What our teacher does is he has this,
Yeah,
how he does.
f of x, and then you go back to f, and then you go back to f of
Yeah.
y, and then you go back to
So I
f.
guess this would this work also?
Yeah, this is much faster.
Yeah, I'm gonna try.
Have you seen Jhevon teaches on his,
Oh, is this what you?
this is what, I'm on YouTube.
and I forgot them again today, so I guess Monday I'll